So not only can we do algebra on infinite power series that represent functions to get new ones, we can also perform calculus. So for instance, if I wanted the power series for 1 over 1 minus x quantity squared, what you might note is that this is the derivative of something whose power series we know. So for instance, 1 over 1 minus x squared, you may recall that's the derivative of 1 over 1 minus x, and we know this power series. So if I want to get a power series for 1 over 1 minus x squared, I'm just going to take the derivative So I want to say, well, 1 over 1 minus x, we know what this is. Right? So I'm just going to take the derivative on both sides, and that'll produce a new one. So the derivative of the left-hand side is 1 over 1 minus x squared. Oops. And the derivative of the right-hand side is 1 plus 2x plus 3x squared plus 4x cubed, etc. So we can get power series through differentiation. By the way, I haven't been doing a good job of writing the general terms. If I wanted to write the general term here, I mean, we might have said, oh, this includes an x to the n, right, as the general term. Therefore, the general term here, since we took the derivative, would be n times x to the n minus 1 as the general term. Okay, so how about the one below it? Well, let's find the power series for 2 over 1 minus 2x squared. So I think I'm going to view that as 2 times 1 over 1 minus 2x squared. I'm going to zoom in a little bit. And the reason I want to do that is because I want to view this as 2 times the power series in which this is like my r value in a geometric, and that's my a value. So this would be 2 times 1 plus 2x, 2x squared plus 2x squared plus 2x squared cubed, etc. And then distribute the 2. So that becomes 2 plus 4x squared. So 2x squared squared becomes 4x to the 4th, times 2 would be 8x to the 4th. The next term would end up being 8x to the 6th, times 2 would be 16x to the 6th. So there's my power series for g of x. So now let's find the interval of convergence for this power series. So if you just again follow the structure of the geometric and note that that we want the absolute value, so interval of convergence. We want that the absolute value of 2x squared, we need that to be less than 1, which means we want -1 to be less than 2x squared to be less than 1. Dividing by 2 yields this. Now a square number is always positive, so the negative 1/2 being less than x squared is not really giving us any information. So I'm just going to write this instead. And square rooting would give us that as the interval of convergence. So my interval of convergence is 0 less than x less than 1 over root 2. So now let's find the power series for g prime. First, let's find what g prime is as a function. G prime of x is the derivative of 2 over 1 minus 2x squared, which I might write as 2 times 1 minus 2x squared to the negative 1. And so that derivative would be negative 2, 1 minus 2x squared to the negative 2. Don't forget the chain rule, times negative 4x, which gives me 8x divided by 1 minus 2x squared. So that power series, that's just going to be the same as the derivative of the power series we found above for g, which is the derivative of 2 plus 4x squared plus 8x to the fourth plus 16x to the sixth, etc. So that ends up being 8x plus 32x cubed plus 96 x to the fifth, etc. So there's our power series for, I'm just going to restate it. So for that function, and the interval of convergence for this guy gets inherited from the other one. Now, I haven't proven that or anything, but it's something worth looking at graphs for rather than look at the general proof. I think it's just better. If you take a look at the graph, you'll see that this equality is only true on the interval 0 to 1 over root 2. All right. So again, we can use calculus to get new power series, and interval of convergence gets inherited from the function you started with. So just as we can take derivatives to find new power series, we can also integrate to find new power series. So for instance, if I wanted to find a power series for the antiderivative of 1 over 1 plus x, I first would want to know what the power series is for 1 over 1 plus x. Now we already came up with that in a previous example. It was that. So to find a power series for the antiderivative, I'm going to write this as, I'm going to take the antiderivative of both sides. Now the antiderivative of the left-hand side is natural log of 1 plus x. I don't need absolute values here. And the reason I don't is because 1 plus x is always positive on the interval negative 1 to 1, which means that we're taking the natural log of a positive number, which is fine. So we don't really need the absolute values. In any case, the antiderivative going term by term gives me, well, the antiderivative of 1 is x, the antiderivative of negative x is negative 1/2 x squared, of x squared is plus 1/3 x cubed minus 1/4 x to the fourth. And let's look at the general term. I'm going to view this as negative 1 to the n times x to the n. So I'm going to view this term right here. So its derivative would be negative 1 to the n x to the n minus 1. That's the general term. Plus c, right? When we take antiderivatives, there's a plus c at the end. So I add that plus c in because we need to make sure, in order to find the c, we just want to make sure that the two sides are equal, and the only time we're guaranteed that they're equal is when you evaluate them at the center. So the center of this power series is 0. So if I plug in 0, when you plug in 0, you get natural log of 1 equals, everything goes away on the right-hand side except a c. So that'll tell you if there's a c that needs to be, is an adjustment that needs to be made. But in this case, it doesn't, because c is equal to ln of 1, which is 0. So the c is equal to 0, so we didn't really need it. So ln of 1 plus x is just equal to this power series here on the right. Let's try another example with different notation. So let's write the power series for 1 over 2 minus x centered at 1. So that is 1 over 2 minus x, and that's going to be equal to 1 over 1 minus x minus 1, which we saw was 1 plus x minus 1 plus x minus 1 squared plus x minus 1 cubed, etc. Cool. So now what we want is the power series for this function, which is an antiderivative of our original. So what I might do is just literally plug in. So we're going to call, obviously this is f of x, so this is equal to the integral 1 to x, and f of x, or f of t rather, was 1 over 2 minus t. But I can write that as its power series, 1 plus t minus 1 plus t minus 1 squared, etc. dt. And now if I apply the fundamental theorem, you take the antiderivative term by term, you get t plus 1/2 t minus 1 squared plus 1/3 t minus 1 cubed, etc., evaluated from 1 to x. And that gives you x plus 1/2 x minus 1 squared plus 1/3 x minus 1 cubed, etc. So that would be when you plugged in x. When you plug in 1, everything goes away. Don't forget the minus from the fundamental theorem. Everything goes away except that you have a 1 at the beginning, right? It would be 1 plus and then a bunch of zeros. Right? And so in the end, you can sort of see why this is happening. This first term, how is it different than the other ones? It doesn't have the minus 1. Well, that minus 1 is going to come from this guy over here. So this minus 1 I'm just going to move out to be in front where this first x is. And therefore we'll get the full even looking power series. So there is our final power series for the antiderivative or an antiderivative of 1 over 2 minus x.